focus on the technology itself. What I'm going to do is to show you how Flownex is equipped to solve the problems or to do designs within this technology. So I'll focus on that throughout this short session. Just a quick overview for everyone. What we are doing, if we are talking about the humid air cycle, here at the bottom would just be a normal air cycle, a gas turbine cycle. So we'll have air coming into the compressor and then going through the combustion process and then through the turbine and then out. Now, the problem with this, or not the problem, the part where we can make it even better than it is currently, is the flame temperature in the combustor is obviously a lot higher than the temperatures that the turbine can handle. So in order to almost, if I can say, cool down the flame temperature, we need excess air through our compressor. And that needs a lot of power to compress in order to get it through the system. So the engineers comes up with a lot of ideas in order to create better ways to have higher system efficiencies. And one of that is in order to rather include water into our system and thereby then save the energy that would have been used to compress all of the air and to have the excess air. So that is in, what do you call it, an overview of what all of this is about. And there's multiple ways in which the engineers have come up with up until now to include the technology of getting vapor into the system, evaporation, sprays, all of that. So, so this is just an overview of what the next 20 minutes will be about. I'm going to show you another image. Just take that bit back a bit. Here's another image. You can see the compressor, and then as the air goes through the compressor, it will go into some box here, and then out of the box back into the turbine. And what happens in this box is there will be some heat exchange, whether through a recuperator or anything in order to increase the cycle's efficiency. But in our case, we will also have the water coming in here, or the water vapor coming in here. And then also, obviously, we need a line in order to include the fuel. So just to show that, in our system, the system that I'll be focusing on now, we will have fuel coming in just before the turbines, and then we'll also have water coming in just after it has been heated and after the compressor. So I'm going to start off with a small network, just focusing on this part, just the water coming into our air system, and then also the fuel coming in up until the point where it enters the turbine. Right, so let's go to Flownex. This is our canvas. This is where we will be working, and I'll quickly show you guys how we would build a small model. So for those of you who've been working with Flownex a lot, just bear with me, and then in this also I'll showcase the capabilities of Flownex. And what I'll focus on in this 5-minute session is to show how to include fluids. Remember, there will be different gases that makes up the air in different concentrations, and then also to include the water into that gas, and then also the fuel. And then through our combustion process, we will then have the combustion product, which will be another combination or another concentration of all of those. So I'll focus on that for now. Okay, so I'll drag in a pipe, and then on the inputs I can quickly give some inputs to it. So let's say a diameter of 0.7, length of 10 meters. This is just an arbitrary system. I can give a roughness of the pipe of say 60, and then I can increment the pipe if I want to for more detail. Okay, like in any system or software that we used in network solving, we also need to add boundary values. So I'm going to get a boundary value. Remember, we are now downstream of the compressor, so I'll add in a pressure of 2000 kPa. So that is a pressure ratio through the compressors of 20. And then let's say temperature of 310, say for instance. Okay, so next up I need to assign a fluid, and I've already created this mixed fluid that I want to use, air combustion. And this then have a combination of several different gases. And I'll get to that just in a moment. So just hold that thought for a bit. Create some space here. And then I'll add another pipe. So just to go back to our image. So we've done this session now where the air comes out of the heater or whatever. And now we'll add some water to it. Okay, so that will be the water line, and then let's just go a little bit further. So I can copy and paste this, whoopsie, I can copy and paste this pipe, and then again have another pipe included. And I can add properties to both these pipes simultaneously by just multi-selecting them, and let's say a length of 2 meters, 0.25 for the diameter, roughness 60, and let's leave the increments at 1. Okay, so next up, I need to add boundary values again. And for the water side, let's say we want a mass flow for the water of 1.5 kilograms per second. Then I can say, fixed on user value, say 1.5, and then also specify a temperature where the water comes in. And then I'll go to the the fuel. And let's say a mass source. I'll specify a mass source of 2, and the temperature of the fuel as it comes in, let's say that will be 30 degrees C. Now, as we speak about that, obviously, you know, and I show this to you, that this will be water and this will be fuel, but Flownex doesn't know that yet. And therefore, we have to find a way to communicate that to the software. And we do this by specifying mass source fractions. So I'm going to change this to yes. And here you will see this is the combination of gases and the fuel that our total fluid will be made up. So we have the typical gases that's in air, and then also we have methane, which will be our fuel, and then the water section. So let's start off. I'm just going to have some representative to air, normal air, and 0.23. So this will be the part that comes in. Here we only have water. So I'm only going to assign water to this one. And there we have all of the mass will be water, and in this case all of the mass will be fuel. So I can say there is methane, value of 1, mass fraction of 1. So now we have air coming in here, some ambient air, and then we have water and we have fuel. Next up, I just want to make sure, quickly make this one a little bit shorter. Next up, I need to add the combustor. And I can do this, first of all, by simulating some kind of pressure loss through the combustor section. And I can do this with, well, I can use any component for that. Let's now take the general empirical relationship component. And the pressure loss behavior will be according to this pressure flow relation. And let's give a constant of 10, 1, and 2. Again, this is just arbitrary values, just to show you how to set up the network and how easily Flownex helps us to calculate the gas constituents. Then I'll add another boundary value at the outlet, and I'll tell the whole system to have a flow of 100 kilograms per second. And then lastly, the combustion process. So I'll take my adiabatic flame, and this component is based on the NASA model for combustion. So, or actually it uses the NASA model. So there's a lot of fuels that is incorporated, and it will calculate whatever we have in terms of temperatures and the combination of the oxygen and fuel ratio, and then it will calculate that the flame temperature and also the products. Okay, this is the scary part for me because now I have to solve this, but I think everything will work. So let's try it. And you can see by all of this is that it works perfectly and it converges perfectly. So let's see what's the temperature there at the outlet. We're now sitting with a temperature of 1102 degrees C, and we came in here, you can see the third from the top at 285 degrees C. Okay, so we have the combustion process, and also what is important if we look at the gas mass fractions. So here we come in, that's the ones that I specified, and here we add more water. So the water mass fraction will change along with the others as well. There you can see that. And next up, we'll add the methane. So if I click on this node, then there's the methane, and you'll see the combination of fluid changes. And then lastly, going through the combustion process, we'll obviously generate some carbon dioxide. And if I click on this node, you can see here that there is the carbon dioxide that has been generated. So this is basically the fundamental, what can I call it, the principle on which you can build the whole system. We have the components in our library, which you can use to model your pipes and your heat exchangers and all the components that's already in your plant. And furthermore, then the capability to simulate a combination of different gases together or different fluids together makes this extremely useful and extremely suitable to the power industry, and specifically now for the humid air turbine technology, and then also the combustion process, and from here we can go through to the turbines. So next up, I'm going to go on to show you a more elaborate model of a humid air turbine cycle. But I just want to pause here for a second and just make sure that everyone is still with me. And if there's any questions, you guys are welcome to quickly pop in, and I'll try to answer them as best as I can. So any questions, anything that's been unclear up until now? Okay, no questions. That's good news. All right, so I'm going to go on, and next up I'll show you a more elaborate network. So let's go to that one. So here you can see a network, and what happens here is we have the air coming in from ambient conditions, goes through the low pressure compressor, and then through an intercooler, heat exchanger, the high pressure compressor, and then we have the water side that comes in. And here you'll see there's an Excel icon, and I'll get to this one just in a second. Okay. After the water section, we go again through a recuperator. So this is a recuperator going to the combustor, where we add our fuel with the combustion process, and then through the turbine, out again through the recuperator, and then there may be some more components here if that is part of the system. I'm not going to model that now. I'm just going to look at this section as it is here. You'll notice that there's two different images for the recuperator and the heat exchanger that I have here. And there's actually, we have quite a number of heat exchangers in Flownex. And each of them, as is with all the components in Flownex, has different levels for its required inputs, and therefore different applications in order determining by which results you're looking for. The intercooler is just a simple heat exchanger. I specify the overall heat transfer coefficient with a number of shell passes and give it some pressure loss characteristics, whereas with the recuperator, it's a more detailed component that I can specify the flow areas and the some heat transfer coefficients, specify the type of material that I'm using. So this is just to show you the different levels of components that we have. In terms of the compressors and the turbines, we use maps in the background. I'm quickly going to go to, say for instance, the turbine. And here you'll see this is the turbine performance map. So we'll have the pressure flow map and then also the efficiency data. And the compressor or the turbine, and the same with the compressor as well, they will then function according to those maps. This allows the system to respond in a real way, in a real world scenario system. So it will go off design and just as it is in the real world. And this is where Flownex comes to its own. So up until now, up until this point where we've done just steady state solutions, I believe there's quite a number of software that does pretty much the same. It may have some advantages, some disadvantages up until this point, but doing just an energy and mass balance is fairly simple in terms of software purposes. But the moment we go into transient analysis or dynamics analysis, and where we calculate according to the flows, we calculate pressure losses, that's a whole different ballgame, and that's where Flownex comes to its own. We also use not only conservation of momentum, conservation of energy and mass, but we also use conservation of momentum. And this allows us to accurately simulate pressure pulses and flow distributions all over the network, which gives us, again, a real-world scenario of what will happen exactly on the plant. So with those three conservations, momentum, energy, and mass, this allows us to do startups through the system, shutdowns through the system, say for instance a turbine trip, or any scenario that you can think of. We can easily model in Flownex in order to represent that. Okay, let's get back to this Excel component that I spoke of earlier. In the technology for humid air turbine cycles, as I explained earlier, there are quite a number of ways in order to get this humid vapor into the system. And you can use your own correlations or determining on the technology that you're using for that, whether it's by evaporation or sprays or a combination of evaporation and sprays or swirl mass transfer. There's a lot of technologies. And you can then use an Excel component like this one, which is the normal familiar Excel interface, in order to calculate that and to get to the exact heat transfer correlation and mass transfer correlation that occurs in this technology. So I'm not going to go in that, just again, a very, very powerful feature within Flownex in order to do whatever you'd like and add commands and correlations which will suit you according to your custom needs. Another component is the control component. So we have a full control library, which allows us to control the system just as we would in real life. And in this case, I will try to control the temperature at the inlet of the turbine to 1200 degrees C by varying the amount of fuel that goes into the system. Okay, everybody still with me? I'm going to set up a transient or create a transient analysis now, a dynamic analysis, and you can see a graph that will go over time. And what I'm going to do with this is I'll change the atmospheric temperature. So the temperature that comes in at this point, and then we'll see what is the influence of on the efficiency. Now remember, as I said earlier, this is just an arbitrary system. So you will see that the efficiencies are quite low for such a system, for the humid air turbine cycle, but that's not the focus. The focus is the capabilities of Flownex that allows you to create this and to create this networks and investigate the networks. So I'll just create a steady state solve again, and then I'll start with the dynamic analysis. And here you can see the values changing, and let's look at the graph. So as time goes on, you can see that the temperature is slowly increasing, and with that we have a decrease of efficiency, just as we would expect in real time. I'm going to leave this for a while so that it goes on, and we'll come back then in just a few minutes in order to do that. What I also want to show to you is at the outlet where we can model other components, and as an example of that, here is just close that one. Here is a network in which a regenerative heat exchanger is used at the end, a regenerative steam generator. And here you can see there we have the steam drum, and we have the water that will come in on this side, and it will change through the two-phase system in order to go to steam and go out again. So this is also a very powerful feature. As Luke said in the beginning, we had a strong focus, especially in the early days, on the nuclear power industry. And everything that is in Flownex is set up in order to satisfy the nuclear industry. And therefore, we have the two-phase models that works perfectly well and is extremely suited for analyses like this. Okay, let's quickly get back to the system, see where our graph is at. Okay, so we still have a slight decrease, in overall efficiency as the temperature increases, and in a moment the temperature will start to go down again. There we go. And we'll also see an increase in efficiency as the temperature goes down again. So just again, this is a very, very basic transient scenario, and you can set up anything, turbine trips, compressor trips, and you'll be able to simulate the behavior of the whole system with the inertia of flows, with the inertia of temperatures that is in our geometries of the heat exchangers, and this will help you to get a real picture of what happens in the network. So just to summarize all of this, I personally believe that the power of Flownex lies in the fact that it helps you to determine the optimal cycle layout and the best suited component performance for maximum system efficiency and operability. So you can see, just again to say this, it's very easy to move around different components to investigate what will be the effect if I take away my intercooler, what will be the effect if I add more heat exchangers. So the maneuverability of Flownex makes it extremely powerful to investigate different system scenarios. Also, I can investigate the system's control strategy and performance with real-world system response. So I can use this tool with its conservation of momentum and use that with the control and everything that's in Flownex in order to see really what will go on in my plant. And then lastly, in our components, we will see here in this side, we have a whole library of third-party software, ANSYS, Relab, MathCAD, and OPC control systems. And we can link to those third-party software if needed in order to have a more detailed simulation. Say, for instance, you want to see have a detailed simulation of the heat exchange within the combustor or some other position. Then you can link up to these software. And this makes it just a powerful package that envelops everything that you would need in order to, or well, most of the things that you would need in order to have a thorough investigation in terms of either research or design of your system, and then later on also when it comes to commissioning, to use this tool to see what goes on in the backgrounds of your network. So that's what I had in mind. Again, just to summarize, Flownex will be ideal, and this is where Flownex is a step ahead of the others in order to determine your optimal cycle layout and the best suited component performance in terms of your heat exchanger side and turbo performance, in order to get your maximum system efficiency and operability, and then also to investigate the system's control strategy and performance with real-world system response. And that's what I wanted to show you guys today. Are there any questions at this stage?
Thank you very much, Rolf. And to everyone who's been listening, thank you for taking the time out. If you do have any questions while I'm speaking, feel free to just raise your hand or drop a question in the question box. We've come to the end of the presentation or the webinar. And yes, very well done, Rolf. That was excellent. It was a great presentation, very enjoyable to watch. If anyone who has attended this, if you would like to comment, or if you would like to make any contact with Flownex, we'd really appreciate it. You can just drop me an email at any of the Flownex email addresses, inquire1@Flownex, or myself, which is luke@flownex.com. We'd love to follow up, and if you are interested in any kind of introduction to the software, we've got video online training. We can offer you a free trial period to just experience the software firsthand. So feel at any time or at any point, you just drop me a mail and make contact. We appreciate your time. And with that, I'm going to say thank you very much and goodbye.
Yes, thanks guys. Thanks for tuning in, and have a wonderful time. Goodbye from my side as well.
Ciao, ciao.
Cheers.